right, so we're looking here for the pH of a 0.030 molar sodium sulfide solution. So first we need to figure out what type of solution this is. And you're not going to find sodium sulfide on any list of acids or bases. This is a salt. So we need to consider what we know about the acid-base properties of salts. So the cation here is the sodium ion. The sodium ion, in terms of acidic properties of salts, is considered the conjugate acid of the strong base sodium hydroxide and therefore has no acid-base effect. So we can ignore the sodium. That leaves the sulfide. So the sulfide ion is, in this system, going to be the conjugate base of a weak acid. And it is the conjugate base of the weak acid, HS minus, which is the conjugate base of the also weak acid, H2S, hydrogen sulfide. So not only do we have a salt problem here, we have a problem that involves an anion of a polyprotic acid. So we are going to need to look up the Ka values for H2S, and there are going to be two of them. So we have Ka1, which is 9.5 times 10 to the negative 8. I got these from my textbook, and Ka2. So Ka1 is going to be associated with going from H2S to HS minus, whereas Ka2 will be associated with HS minus going to S2 minus. So which of these are we interested in? Well, at first glance, the system we're interested, the substance we're interested in is the sulfide ion. So we actually need Ka2 to do this problem. So we're also going to need, because this is a base and these are Kas, we're going to need to change between Ka and Kb. So we're going to need our Ka times Kb equals Kw equation. So we're going to need to find the Kb here. And when we do that, if we take 10 to the negative 14 divided by the quantity 1 times 10 to the negative 19, that actually equals 10 to the 5th, which is way, way, way larger than 1. So what we know about equilibrium is that when we have a equilibrium constant that is several orders of magnitude larger than 1, it means that that reaction goes essentially to completion. So we can assume that all of the S2 minus will in fact undergo a first hydrolysis reaction and be converted to HS minus. So it turns out to solve this problem, we actually need the Ka1 value because we're going to need to it's going to be the equilibrium between H2S and HS minus that actually determines the pH of this solution. So we need to do the same calculation again. So now it's 10 to the negative 14 divided by the quantity 9.5 times 10 to the negative 8. And that is 1.05 times 10 to the negative 7. Okay, so that's going to be our Kb value. So once we have a Kb value, then it is time to set up our ICE table, which I actually like to call a rice table because R is for the reaction. So what kind of reaction is this? Well, this is the hydrolysis, and we're using the Kb that is associated with the change between HS minus and H2S. So we want to write our equation like this, the hydrolysis of HS minus. So, okay, what are our initial values? Well, we start with all of the originally S2 minus because we said that that first step went totally to completion. So we end up with 0.030 moles. H2O is a liquid, so we can ignore it. It does not appear in the equilibrium. And we start with none of hydrogen sulfide or hydroxide. What's going to happen? Well, we're going to lose some amount. That's still a liquid. And we're going to gain that same amount over here. So where do we end up? 0.030 minus x, x, and x. However, we're going to assume that 0.030 minus x is approximately equal to x, because 2.030, sorry. Because with the magnitude of the equilibrium constant that we're dealing with here and the number of significant figures we have, that subtraction is going to be so small that it would round right back to 0.030. So now we need our equilibrium expression. If you're asking this question, I'm assuming you already know how to construct that. So you shouldn't be surprised to determine that we end up with 1.05 times 10 to the negative 7 equals x times x divided by 0.030. So if we solve for x, we get 5.6 times 10 to the negative 5. And remember, that is going to equal the concentration of hydroxide ions. So again, if you were asking an acid-base question of this level of sophistication, I'm going to assume that you know how to get from the concentration of hydroxide ions back through to the pH. The tough part of this one isn't that, it's figuring out the fact that this first step goes to completion, and so we actually need to use the Ka1 value to figure out our pH. Hope that was helpful.